The last couple times last week, we talked about carbon concentrations in the atmosphere and the carbon cycle. So we're releasing CO2 from fossil fuels. It's accumulating in the atmosphere. We talked about where it goes and how it's cycling around the system. And now we're moving on to what that actually does to the Earth's energy budget and how that then changes temperature of the Earth. So the main idea, I mean, where we're going with this is we want to know what causes global temperature to change in detail. And so this is a diagram of estimates of global temperature, or I guess this is northern hemisphere temperature, so close to global, half of the globe, over the past 1800 years. So from the year 200 to the year 2000. And so we can see the temperature goes up and down over kind of various timescales. You have it kind of going up and down on decade to decade timescales, and broadly on century timescales, getting a little bit warmer and then cooler. And then up to the year 2000, since the Industrial Revolution, has been going up, up, up. And so that's what the topic of this class is about. But you know, we want to understand why temperature changes in general and what causes global warming. And so we can think about this in a number of ways. So we want to just get to like the baseline fundamentals of what causes climate in the first place. So, you know, one way to think of that is like just what causes temperature to vary from place to place in the first place. So this is a map of annual mean temperature. So that means that it's annual mean means averaged over the seasons. So summer, winter, spring, fall, average temperature over the entire year. And so, of course, you know, where it's hottest tends to be near the tropics, near the equator. And then where it's coldest tends to be at higher altitudes and higher latitudes. And so there's like some clear, you know, pattern underlying this. So in particular, the latitude aspect is what will come into play in this class. But so this is a thought-provoking question, you know, what causes temperature to vary in the first place? And so we can think about, okay, temperature varies in space, it varies horizontally, but it varies in other ways that we're familiar with, right? So it varies from day to night. So the day tends to be warmer than the night. So here's just a picture of the sunset or sunrise, or this would be sunset, probably transversing Europe. And we know that when the sun comes out in the morning, here's just a little graph of temperature over the hours of the day. When the sun comes out in the morning, it gets warmer. Then we have a kind of peak in temperature, which doesn't actually occur when the sun is highest in the sky. It's a little bit delayed. And then temperature comes down. And then when the sun goes down, it continues to go down. And you have kind of a minimum of temperature right before the sun comes up again in the morning. So that's just another example of something that we're very familiar with, temperature varying. And then probably the other example that's most familiar is our seasonal cycle, that summer is warmer than winter. So here's just some graphs of the United States monthly average temperature in the winter in January, and then monthly average temperature in July. And then that's averaged over 1979 to 1995. So you have to have some long period of time that you're averaging over to get at like a climate type signal. So these are both on the same temperature scale. And we can see, this is degrees Celsius, but we can see that, of course, it's warmer in the summer than in the winter. And there's some other interesting features that we may talk about at some point, like that there's a lot more variation in our winter temperature than in the summer. But that's not important right now. What I'm trying to emphasize is that we're familiar with a bunch of temperature changes. What we're not so familiar with is long-term climate changes, which is what we're learning about in this class. But it turns out that these are all kind of caused by the same underlying fundamental physics. So one last highlight of temperature changes that we're familiar with is just kind of putting it together on a location by location basis. So if we look at the climate of San Jose versus the climate of St. Louis, Missouri versus the climate of Minneapolis, Minnesota, we can kind of pick out some interesting variations. So first, San Jose climate. This is the daily average high temperature in degrees Fahrenheit and the daily average low temperature in degrees Fahrenheit at the top for each month of the year. So what this means is that in January, on average, our afternoon high temperature is 59.3 degrees, and our afternoon or our morning low temperature is about 42 degrees. And so we can see all of these variations kind of going on at the same time now that we have our seasonal cycle. So it's, of course, it's warmer in the summer for both the afternoon high and the morning low, and then colder in the winter. And if we look at this compared to other locations, looking at St. Louis, we didn't really change like our latitude when we went to St. Louis. San Jose and St. Louis are roughly at the same latitude, but we do see some differences in our temperatures. So it tends to be a little bit warmer in the summer in St. Louis. So we're at close to 90 degrees in July instead of 84 degrees in July in St. Louis. But then it's much colder in the winter. So 38 degrees Fahrenheit for a high in January compared to 59 degrees Fahrenheit in, 59 degrees Fahrenheit in San Jose compared to 38 degrees Fahrenheit in St. Louis. So colder in the winter in St. Louis, a little bit warmer in the summer. That's interesting. If we go up to Minneapolis, so now we are increasing our latitude closer to the North Pole, then we see, okay, the summer, it tends to be pretty warm still, so 83 Fahrenheit and an average morning low of 63 Fahrenheit. But then in the winter, we're really cold, 22 degrees Fahrenheit for a high temperature on average, and an average low, is 4.3 degrees Fahrenheit. So this is where I'm from. I'm from Minneapolis, Minnesota, and January is not fun to live in Minneapolis, Minnesota. It's just dry and cold, and because it's dry, we don't tend to have a lot of snow days. Like you don't get a lot of days where there's like 3 feet of snow and then you don't have to go to school. But because it's so cold, a lot of times you'll get like weeks at a time where the high temperature is not above 0. And so then they'll say, okay, you don't have to go to school because if we have kids waiting out at the bus stop, then you might freeze to death. So stay home because of that. So we get cold days, but not snow days. But so the whole point of this introductory thing is just that there's a bunch of variations in temperature, and they're all actually explainable by these simple concepts that we're going to be talking about today. So they basically go back to this diagram that I already showed. So this diagram that we've been talking about with the energy budget, and we discussed in the overview of climate science, that we have this energy coming in from the sun. We have energy reflected, shortwave radiation reflected back to space, and we have outgoing long-wave radiation from the surface of the planet. So we are going to be breaking these down using an equation. So these are our, this is kind of the outline of what I'm going to be talking about for the rest of class today. These are the conceptual tools. So each one of these phrases down here is essentially a conceptual tool that we will use to make sense of variations in temperature generally. So it's not that seasons are explained by one theory and day-night temperature is explained by another theory of temperature, and then climate change is explained by another theory of temperature. They all basically go back to the first law of thermodynamics. And then the first law of thermodynamics will go through each one of these individually. We have to understand basically just the definition of energy, the definition of temperature, and then the definition of heat capacity. So here is our equation for the first law of thermodynamics. This is the first law of thermodynamics. It says that a change in temperature of essentially anything is related to the energy flowing into that thing minus the energy flowing out of that thing, divided by the heat capacity. So this is definitely something that you're going to have to know for the test. You're going to have to be able to like say this in words. So equations are just nice shorthand, compact ways of explaining very important relationships. And so this equation can be then, translated into words. And the words are just a change in temperature has to do with three things. It has to do with the amount of energy flowing into that thing, the amount of energy leaving that thing, and the heat capacity of that thing. So let's talk about each one of these components. So first we're talking about energy here. This is a thing that we'll talk a lot about in this class in a lot of different, kind of under a lot of different circumstances, a lot of different seemingly unrelated circumstances. And so it's useful here to actually take a step back and define what energy is. So energy is officially the ability to do work on some form of matter. So, unfortunately in science, as soon as you define something, then you have these other pieces of jargon that you have to define as well. But so in this case, matter is anything that has mass and occupies space. So things that you can hold and throw and move around. And then work is a specific definition in science and physics. And work is done, it's defined as something that happens. So work is done when matter is moved. So if it's pushed or pulled or lifted over some distance. So this person pulling this car is doing work on this car. So energy is just something that is going to cause matter to move. So if you're seeing anything moving, there's some, energy, or you're seeing something, essentially if you're seeing something moving, you're seeing energy, the result of energy. So energy is a little bit weird to define because I think it's very intuitive to define matter as being things, but energy is kind of defined in terms of what happens, and there's just no way around that. That's just what it is. It's the ability to do something, to do work, to move matter around. So we have several units of energy that we use in climate science. So you may have heard me mention a joule before. So a joule is the kind of standard, international standard unit of energy that's used in all of science. But it's the same as units of energy that we're more familiar with, like for example, a calorie. So a dietetic calorie, the calories that you see on food labels are units of energy as well. And so you can just convert these. So one dietetic calorie happens to be equal to 4,184 joules. So the point of me putting these numbers up here is not like, oh, you have to memorize that or something. It's just to emphasize that when I say a joule, it's the same thing as a calorie. It's just you would just convert them by multiplying it by 4,184. So a watt is the other unit of energy that I'll talk about a lot. And we talked about watts in the energy budget diagram before, how many watts were coming in from the sun versus how much was leaving. And a watt is just a rate of energy movement. So it's a flow. So we're going to be talking, is very similar to the carbon cycle. We're going to be talking about kind of reservoirs, stocks of energy, just like we had reservoirs and stocks of carbon, versus flows, which have a unit of time in the denominator, right? It's a flow. With the carbon cycle, we're talking about carbon movement per unit of time. And with temperature and energy, we're talking about units of energy per unit of time. So we're moving joules around per unit of time. That's what a watt is. It's a joule per second. So a 100-watt light bulb, for example, is a light bulb that is emitting and consuming 100 joules per second, and emitting that in the form of heat and light. And so with these kind of conversions, you can say, okay, a 100-watt light bulb burns 86 dietetic calories per hour. You just convert seconds to hours and joules to calories. And this, by the way, is about what people burn. If you think about like a person burns around 2,000 calories a day, if you do the math on that, that's about 100 watts as well. So we're all just sitting and burning about 100 watts just from sitting and living our lives. So we have calories coming in, and then we're metabolizing them, and then we're releasing that energy as heat and using it to move around our bodies. And this will not be important for the rest of today, but it's just something to bring up what we're talking about energy, is that when we talk about energy consumed for electricity, for example, you'll see the unit of kilowatt hour. And so kilowatt hour is just 1,000 watts times hours. It's kind of this weird unit, but basically it's just a unit of energy as well. So it's 3.6 times 10 to the 6 joules. So 3.6 million joules. And so when you see these kilowatt hours on your energy bill, that means just how much energy you consumed during that billing period. So over a month, how many joules you consumed. So watts tend to be what we use when we're talking about the energy budget. So going back to this energy budget slide here, I use watts per meter squared. So I'm taking the joules coming in from the sun, dividing it by seconds, so it's a rate of energy movement. Whenever you see an arrow, it tends to be a rate of movement. And then we tend to divide it by the surface area of the Earth so that it's per meter squared, per square meter. So energy takes on many different forms and it moves around, but the total amount of energy in the universe is constant. And so just like with carbon, we talked about carbon as a conserved thing. We don't create or destroy carbon on Earth. Energy is the same. Energy cannot be created or destroyed. It gets a little bit tricky when we're talking about nuclear energy because you're converting mass to energy with E equals mc squared. But on Earth, it's pretty simple. And it's just that, and this, it follows the first law of thermodynamics, which is what we're talking about today. And basically, we are never creating or destroying energy. So just an example of the movement of energy, the one that we've talked about already, energy coming from the sun, that is actually mass being converted into energy through nuclear reactions that flows to the earth. Our primary producers, our photosynthetic organisms, our plants, capture that energy and store it in the bonds of the molecules of the plants. Then animals eat those plants, and then animals higher up on the food chain eat those animals or eat the plants directly. So humans eat the animals or the plants. And so this is just the movement of energy coming from the sun, empowering our bodies. And so then just to put our familiar equations back up here, photosynthesis and respiration. Before we were looking at these equations, emphasizing that we're not creating or destroying carbon. So there's like 6 carbons over here, and you see that there's 6 carbons over here, and there's 12 hydrogens over here, and there's 12 hydrogens over here. So those are conserved, but also the energy is conserved too. So the energy coming in from the sun that is then stored in the bonds of these molecules, that same amount of energy is then released through respiration to power our bodies. So conserving energy, conserving carbon. Okay, so a little bit more on energy. So we have some broad categories of energy. We have potential energy. So that's kind of stored energy, that could be released at some point in the future. And so an example of potential energy would be what we're just talking about, food, the energy stored in the bonds of the molecules of food. So those hydrocarbons. Another form of potential energy would be the energy stored in the bonds of the molecules of fossil fuels. So coal, oil, and natural gas have energy stored in the bonds of those molecules. And then the other broad category of energy that's much more important for our discussion today of the first law of thermodynamics and temperature is kinetic energy. That's energy from the motion of an object. So that's kind of intuitive that things that are moving around have a lot of energy. So like in physics class, they tend to talk about kinetic energy a lot with like roller coasters. And then even potential energy comes into play with that as well, that when the roller coaster is at the top, there's a lot of potential energy that could be released, and then it's converted into kinetic energy as it starts moving, and then it can be converted back into potential energy. So that illustrates 2 concepts: conservation of energy, that you're not creating or destroying energy, you're just kind of changing it from one form to another. But then kinetic energy is the energy associated with movement, with the movement of objects. And it turns out that temperature is directly related to kinetic energy. Here's one example. Here's another example of kinetic energy. If you have movement of water in a river, we could potentially capture that with a hydroelectric dam. And that's just illustrating that there's energy within that water that you can capture to power our cities with electricity. So kinetic energy is what's important for temperature. And I will show you why that is. So this is our second definition in our first law of thermodynamics that we need to understand our first law of thermodynamics. So we have to think about, okay, what is the definition of temperature? So here is what kinetic energy is officially in terms of an equation. It's the mass times the velocity squared divided by 2. So that is telling us that kinetic energy is related to motion because we have velocity over here, velocity, speed, movement. That's not something you need to memorize the equation or anything, but just you have to know that the faster something is moving, the greater its kinetic energy. So that's pretty intuitive. And then the big punchline for temperature is that temperature, the definition of temperature, is the average kinetic energy of the molecules in a substance. So essentially the average speed of those molecules. So, we know that air is made up of all of these molecules, mostly nitrogen, oxygen, argon, and a little bit of CO2, a little bit of methane, these other gases, but they're all moving around. They're moving around really, really fast, actually. But the faster they're moving, the higher their temperature. So we just happen to perceive faster moving molecules as being warmer. That's what our senses tell us. But really what we're measuring is the speed of those molecules. So what's important about this is just that temperature is a measure of energy. So if you increase energy of the Earth, you're going to increase the speed of the molecules, you're going to increase the kinetic energy, and that increases temperature. So then the third definition of our first law of thermodynamics that we saw in our equation is heat capacity. So heat capacity is how much energy it takes to increase a substance's temperature. So this seems like kind of an obscure thing at first, but this is actually pretty intuitive as well. So just to give you a concrete example, guess which one of these has a higher heat capacity? A pot of water or a swimming pool? So the right way to think about this is that if you have, 500 joules of heat, and you put that either into your swimming pool or you put that into your pot of water, which one is going to react more to that 500 joules of heat? And which one is going to react less to that 500 joules of heat? So the pot of water is going to react more. It's going to increase its temperature more because it has less heat capacity. It has less capacity to take in that heat. And so more of that heat is distributed amongst the smaller number of molecules, and it raises the average kinetic energy of those molecules easier, just because there's less of them. There's way less molecules in there, so there's less heat capacity. And putting that 500 joules of heat into your swimming pool means there's way, way, way more molecules in there, so that same amount of energy is distributed amongst a way larger number of molecules. And so it's not going to increase the temperature because the temperature is the average speed of those molecules. And so it can't increase that as much. So here's some other heat capacity examples from our day-to-day lives. So thinking about these two examples, why does the kitchen tile feel colder than the air in the morning? And similarly, why does 60-degree water feel colder to your skin than 60-degree air? So if you get up in the morning and your kitchen is 60 degrees, you may walk out with bare feet and your feet feel really cold, but the rest of your body doesn't feel really cold. And it's not because the tile is colder than the air. They're the same temperature because they've been sitting in the same temperature all night. And same thing with San Francisco here. A lot of times the air temperature is about 60 degrees. The water temperature can be around 60 degrees. Let's just say they are the same. If you're standing outside in 60-degree air, you're fine. You may be a little chilly. But if you jump in the water, you are freezing, right? And so what's going on there in both of those cases? So in both cases, your body is warmer than the environment. So in all four things, if we're talking about kitchen tile or the air or the 60-degree water or the 60-degree air, your body in all those cases is close to 100 degrees Fahrenheit, 98 degrees Fahrenheit internally, but even your skin is much warmer than all these things. And so in all these cases, your body is trying to essentially give off heat to the environment, because we have a concept called thermal equilibrium, where two things of different temperature try to meet in the middle, essentially. So your body's trying to give off heat to the environment, but it's going to do that much quicker, much easier, if there's like a ton of molecules to soak up that heat, something with a high heat capacity. And so that's what's happening when your feet are touching the tile, is there's a bunch of molecules that are at a lower temperature than your body. And so the heat can flow very quickly from your body into that tile. And it doesn't do it nearly as well with air. So we call air like an insulator, that it doesn't allow for the movement of heat very easily, just because it's very dispersed. There's just way less molecules. And so you are transferring heat to the air like all the time, but it's just not very efficient. And it just becomes much more efficient when it's a higher heat capacity thing. Yeah, so we can think of it like more molecules is higher heat capacity. And someone said cold is just a lack of heat. That's a very good point. In physics, there's no such thing really as cold. There's just how fast are molecules moving. They can be moving zero, not moving at all, and we call that absolute zero temperature. Or they can be moving faster than zero, and then it's just how fast are they moving, and that's how much temperature there is. So that's why our real physical temperature scale, Kelvin, goes from 0 and goes up. It only has positive numbers. It's totally meaningless and confusing to talk about negative temperature from a physical standpoint. There's no such thing as negative temperature from a physical standpoint, just like there's no such thing as negative length or something. Okay, so those are our 3 things of our energy budget. We talked about temperature, we talked about energy, and we'll talk a lot more about this specific type of energy that's causing the Earth's energy budget to change, electromagnetic radiation. But we're talking about energy in general and heat capacity. So this is our summary of our first law of thermodynamics. Change in temperature has to do with 3 things: energy in versus energy out versus heat capacity. And we'll often call this thing on top, or actually kind of this whole term on the right, the energy budget. And I just wanted to show how this is just exactly analogous to the typical way that we use the word budget, so a financial budget. So just to flesh out this analogy, let's say we're talking about the budget of a family. So a family of 4, and let's just put some round numbers on it. Let's say the family has $10,000 in savings. So then they have $2,500 per person. So they have an average per person. And they have some income. They make $300 per day. Anytime we have an arrow in this class, we're usually going to have a time in the denominator, $300 per day. And then they have some expenditure. Let's just say they spend $100 per day. So now we can see we have an imbalance in our budget where we are making more than we are losing. So that means our wealth increases by $200 per day or $50 per person. And so all these numbers here are just exactly the same as what we were talking about with the energy budget, just different things. So the energy in the energy budget is like the money, and the energy budget is the financial budget. So we have the money flowing in minus the money flowing out is what we call our budget. And then what would temperature be? The family accumulates 200 per day. But what I'm getting at with the temperature is, we go back to this slide, temperature is essentially that energy averaged over the number of molecules in the substance. So that's why we said, the pool has a larger heat capacity than the pot of water because there's more molecules in there. And then the temperature change is going to be less for a given amount of energy accumulation in the pool than it would be for the pot of water, because you're averaging over more molecules. So in the analogy, temperature is this number. It's the per person. It's the average wealth per person, because you average the energy or you average the money over the number of people in the family. So that means the heat capacity is like the number of people. So this should help with the concept of heat capacity and the pot of water versus the pool. That, like, let's just imagine that we have the same situation. We have more coming in than leaving. So more money coming in than leaving, or more energy coming in than leaving. If we have a situation where we have more people in the family, then your dollars accumulated per person is less, right? Because you're dividing that same amount of energy imbalance amongst more people. And so you're not going to increase the wealth per person nearly as much. And so the exact same concept applies to the pot of water versus the pool, that if you have some imbalance in energy where you're accumulating energy time step after time step after time step, if you have more molecules that you're dividing that energy out amongst, then your increase in temperature is less. So if we're thinking about temperature as wealth per person is analogous to temperature, there's only 3 ways to change the temperature or to change the wealth per person. And so what are those? We can basically change our 2 flow rates, or change what? Or the number of people. So if all of a sudden the family, So in order to change the wealth per person, you could do 3 things. You can change the amount of money the family makes. You can change the income. You can change how much they spend. You can change the expenditure. Or you can change the number of people in the family. So if you have a situation like before, where then all of a sudden they have twins, and so there's 2 more people in the family, it goes from, instead of 4 to 6, then you're going to change your accumulation per person from $50 per person per day to $33.33 per person per day. And so if you were to increase the heat capacity, that would mean that you're going to decrease how much your temperature is increasing per unit of time in the same exact way, just because that same amount of energy is distributed amongst more molecules. So if we put this into an equation form, you can see that they're like exactly the same. So this is the one we have been talking about, change in temperature equals energy in minus energy out. So our difference in energy accumulation divided by the heat capacity. And in our analogy, it looks exactly the same. Change in wealth per family member equals the money flowing in minus the money flowing out divided by the number of people in the family. So this could have either confused you more or been helpful. I hope that it is helpful. If not, then you can ignore the financial budget part of things. Okay, so hopefully it's helpful, especially with the heat capacity part. Is that heat capacity is just kind of the number of molecules, and so it's harder to increase the temperature if there's a lot of molecules. Yeah, this is just one extra point about a balanced budget, right? A balanced budget means energy in equals energy out. So you're not accumulating money in your financial budget. And so we'll talk about an imbalanced energy budget is what we have right now, where we are accumulating more energy than we're losing. And so that's why our temperature is increasing. But so a balanced energy budget would be the same thing, that energy in equals energy out. And so then under a balanced budget, it doesn't mean you don't have any wealth. It doesn't mean you don't have any temperature, but it means that your temperature is not changing. It's not accumulating or losing anything per day. So your change is 0.